So exercise 35. Firstly, recall that in exercise 34, we'll prove that given G module M, if the topology is discrete topology, then there is a characterization of this action being continuous. This section from the product of G with M to M, mapping pair G M to G acting on M, with the product topology on the product of G and M. The first characterization is that any element small m in this G module M, the stabilizer denoted by Gm is an open subgroup of G. The second characterization is that this G module M could be written as a union of fixed point under open subgroups of G, which means it's a union of M fixed point under U. You go through all the open subgroups of G. This is exercise 34. So exercise 35 is a continuation of this exercise 34. Suppose we have a family of discrete G modules. So indexed by I. First remark, or first exercise, the direct sum of this AI is again discrete G module. So you have to tell firstly how is the G module structure, which means what is this topological orbiting group, which is obvious. What is the G action? And then if it is a G module, why it is discrete, which means when you know this direct sum with discrete topology, why the G action is continuous. So here the G action is G acting on element of this direct sum, defined to be G acting on each component. Second part of the exercise. This is not necessarily true. Not necessarily true for product, which means in the first exercise we say that when this is a direct sum, this is true, but this is not necessarily true when you replace this direct sum with the direct product, with the product of G modules. Thirdly, the tensor product of two discrete modules, two discrete G modules, is again a G module. Of course, you have to tell what is the G action. So by G action on the generator to be diagonal action. Fourth, consider the home set. Which I mean home set as Z modules is abstract G module. Abstract means not necessarily discrete. By again, what is action? Action is acting on homomorphism. J compose phi compose J inverse. In other words, J of phi acting on any element small a, big A is defined to be J phi J inverse acting on A. And we claim that the J invariant subgroup equals actually the J equivariant homomorphism formula to be, by which I mean all those Frobenius such that all those morphisms such that G phi equals phi J for any J in J. Lastly, if this first discrete G module A happen to be fixed by some open subgroup U, then we claim that this abstract G module become discrete G module. In particular, it is the case when J is finite or when A is a finitely generated Z module. Okay, let me start proof. So firstly, this obviously gives a G module structure. We have to check whether this is discrete. So this is equivalent to check. We use the two characterizations given in exercise 34. So I'm going to check for any alpha I in the module M. This is our module M. The equalizer is open. Notice there is a finitely many G alpha I not being the whole group, because finitely many non-zero. So G0 would be of course G, and so there is only finite intersection, removing those G alpha I such that alpha I equals 0 imply that G alpha I equals G, and so this is again open of G, and so the action is continuous using the exercise 34. Secondly, for the product, so which would obviously this is possibly infinitely many intersection, and not necessarily being open in G. So this is not very rigorous and thorough proof. To prove that, you should give a counterexample and just give the idea. Okay. So this may not be open, the stabilizer, because this is a chapterization. If there exists some element, the stabilizer is not open, then this will not be continuous junction. Of course, you have to construct a counterexample. So exercise give a counterexample. Thirdly, about the tensor product. So this tensor product, although it's not obvious to look at what is the stabilizer element, right? Let's look at the generator. So we don't know what is stabilizer of a tensor B. Right, it's not obvious, although obviously it contains stabilizer of A intersection with stabilizer of B, but we don't know what is the precise description of this. But however, that's not necessary to describe that. Well, it's enough to say that M equals union under some U go through opens of G, right? So we take any element here. Let's look at the generator. Then notice that it is contained in the fixed point under, let's call this J intersection with U. B, U, A tensor B. It's contained here, right? Because JA fix A, JB fix B, and so their intersection is again open subgroup fix A and B. Let's finish the proof. Lastly, look at this homomorphism. So firstly, this action is described clearly, so we could say that this is by definition all those homomorphisms such that J phi J inverse equals phi any J in J, and so this is the same as homomorphism such that J compose phi equals phi compose J any J in J, and so this is the same as J equivariant homomorphism, right? And so now let's discuss when is it discrete J module. So if A happen to be fixed by some open and B happen to be fixed on other second open U, when U2 both open J, then I would claim that so for any phi in homo JAB, it is contained in, again, the points fixed under the group. Let's call it UJ, defined to be U1 intersection with U2. Why this is the case? Because for any J in U1 intersection with U2, so in particular reduction is trivial on both A and B, then J acting on phi would be J compose phi compose J inverse. And as a map, this would equal phi because for any A in A, J phi J inverse A would be J phi of A, and because J is also trivial acting on B, so this is phi of A. But actually, if you notice, I put something stronger than what is required at the beginning. So at the beginning, we only know that I'm only saying that if A equals AU, I didn't say what about B. So if I know in B has the same condition, then this is okay. If B is not, so put exercise. Can you remove B equals BU2? If this U2 open. G, can you remove this AND condition? So in particular, for the case when J is finite, this is trivially true because when J is finite, it has discrete topology. So in that case, both G and M have discrete topology, so it's always continuous. Nothing to say. The second example is said when A is finite as Z mod U, so let me write as Z mod U, it is of this form. Then in that case, I would say this is still okay. In that case, I'm going to take Uj. I don't have U2, I have U1, which fixes all the elements of A, but I don't know if it fixes elements of B or not. Let me take intersection of stabilizer of phi of E1. Phi of E1, this is in B. So for any element of B, because B is discrete, it has a stabilizer which is open. Intersection with G phi of E2, phi of ED. And so I'm doing this, then take any element here, G acting on phi. I will claim that this is again equals phi, because this is equivalent to say J phi J inverse A equals phi A for any small a in big A, because what do you have to do? You have to check firstly. So you take your element here, so in particular it's fixed element of A. And so it's left to check J fix phi A. But notice J fix phi E1, phi E2, and phi D. So whatever A is, A would be some A1. So let's say N1 times E1 plus N2 times E2 plus ND times ED. So this NI, that's integers, right? And so phi is Z linear, so this would be N1 phi E1 plus N2 phi E2 plus etc. ND phi ED. And so because phi, yeah, so J acting on that would be J acting on this, and would be J acting on this, and J fix all those phi E1, phi E2, phi ED, and so finally this is the same as phi of A itself. I'm saying that written A equals, because there's finitely many generator, written A as Z linear combination of those generators. And so it works again. This is telling you that again we have any phi in home ZAB, phi is contained in fixed point under some open UG defined to be U1 intersection with J phi E1 intersection with J phi ED, which is a finite intersection. And so this is open in J. And so we are done.